Hello everyone, welcome back to the Modeling Guy. Today we are diving into one of the most debated choices in finite element analysis, penalty versus Lagrange methods for constraint enforcement. Which method should you choose for applying constraints in your finite element models? In this video, we will break down the differences between penalty and Lagrange methods and help you decide which one fits your simulation the best. Stay till the end for practical tips on choosing the right method for your model. In finite element analysis, we often need to apply boundary conditions or constraints to simulate real-world behavior accurately. For example, this could mean fixing a node, enforcing symmetry, or applying contact conditions. These constraints ensure our model behaves as expected, just like this node that you see in this slide here, which is restricted from moving in certain directions. But simply forcing these conditions directly in your model can backfire. It might make your system too rigid or worse, unstable. And in some cases, or many cases, it leads to numerical issues that affect simulation accuracy or even cause solver failures. So we do need smarter ways to enforce constraints like the use of penalty or Lagrange methods. To overcome these challenges, we typically use one of the two main approaches in finite element analysis. It's either the penalty method or the Lagrange multiplier method. Each has its own strengths, trade-offs, and ideal use cases. So the biggest question is, how exactly are the penalty and Lagrange methods different? Let's break it down into 10 key differences so you can clearly see when and why to choose one over the other. So let's first start with the core philosophy. The penalty method enforces constraints approximately. So what it means is by adding a penalty when deviations occur. Think of it as giving the system a gentle nudge back to where it should be. On the other hand, the Lagrange method enforces constraints exactly by introducing extra unknowns called multipliers. It ensures the constraint is satisfied with precision. Now let's look at the math behind each method. In the penalty method, we modify the stiffness matrix by adding a large term, alpha times the C transpose times C. This penalizes the deviation and stiffens the system. So you are adding an additional stiffness to the system to account for this constraint. In contrast, the Lagrange method expands the system of equations, so it basically adds both the constraint equations and new unknowns called Lagrange multipliers into the matrix formulation. When it comes to additional unknowns, the penalty method keeps things simple. No new variables are added here. But with the Lagrange method, we add one Lagrange multiplier for every constraint. This means the system size increases, sometimes significantly in larger models. Similar to the core philosophy, when it comes to the constraint accuracy, the penalty method is approximate. How close you get depends on the penalty parameter you choose. If you choose too low and it's inaccurate, if you choose too high, it might cause numerical problems. The Lagrange method, however, is exact. It satisfies the constraints to mission precision. No compromises there. When we use large penalty values, the penalty method can make the system matrix ill-conditioned. This can cause numerical instability or slow convergence. The Lagrange method, however, forms what's called a saddle point system. That means it has both positive and negative eigenvalues. It may be indefinite, but it's usually better conditioned and more stable in practice. So when it comes to implementation simplicity, the penalty method is generally easier to implement. You basically just modify the components of the stiffness matrix. You don't add extra equations. The Lagrange method, however, is more complex. It needs a mixed finite element formulation and adds extra equations to the system. So when it comes to convergence, the penalty method usually converges faster because the system it creates is simpler and smaller. The Lagrange method may take longer to solve. It introduces more unknowns and might need some special solvers basically that are really designed for saddle point systems or the complex matrices. Next, let's look into the robustness of these methods to ill-posed constraints. Before going forward, let's first see what ill-posed constraints really are. So these are basically constraints that are wrong, conflicting, or redundant. For example, let's say you're trying to fix the same point in two different ways or applying more constraints than needed. These issues can break your simulation, so the method you choose must handle them carefully. So, when dealing with these ill-posed or conflicting constraints, the penalty method is generally more flexible and forgiving. It may still run even if the constraints aren't perfect. The Lagrange method, however, is stricter. It expects your constraints to be clean, consistent, and well-defined. Otherwise, the solver might fail or return unstable results. So now let's look into the differences in terms of physical interpretation. The penalty method basically mimics the constraint by adding a very stiff spring. It resists any motion that violates the constraint, but it doesn't stop it completely. The Lagrange method, however, works differently. The multipliers act like an exact force, just enough to enforce the constraint with no extra stiffness added. So, coming back to the first question, when should you use each method? The penalty method works really well for soft constraints and contact problems where a bit of flexibility is acceptable. The Lagrange method is best for hard constraints, multiphysics coupling, and situations where accuracy is absolutely critical. Hope these differences really clarify things for you. In the end, basically choose the method that matches your problem's need for precision and performance. Remember, the art of modeling isn't about making things complex. It's about choosing the right simplifications. Thanks for watching and keep modeling smart. Alright, that's it for today, guys. Thanks for watching again. If you found this helpful, don't forget to like, share, and subscribe for more finite element analysis tips on modeling breakdowns. Got a question or a topic you'd like covered next? Drop it in the comments and I read every one.